Okay, let's review. From a reverse engineering point of view, we start with a circuit. We start down here at the bottom, and what we do is we trace all these wires in here to create these equations up here at the top. From a design engineering point of view, from starting at the top, working our way down, we would be at the excitation table. We would have created these equations here, and we would be entering them into a simulation package like Logisim. Now what we're going to do is we looked at this for mealy. Here's a Moore circuit coming in. We can tell it's a Moore circuit because the outputs have as their inputs just the flip-flops. X and Y have to flow through these two flip-flops in order to influence the output. This is Moore. And again, we're working with the equations that come out of an analysis of the excitation table. Now we're going to go back to mealy. And we can see that we're at the excitation table now of mealy. Our goal is to use these equations to create the excitation table. So how is that done? So let's look at Z. So this is the equation of Z right here. So we look at this and we look at this. So Q1 is a 0. Q1 bar is a 1. Q2 bar is a 1. X bar is a 1. X is a 0. 0 and 1 is a 0. 1 and 1 and 0 is a 0. 0 or 0 is a 0. So that's why that's a 0. So we do that over and over and over again. Let's do one here for D. So Q1 is a 1. Q2 is a 0. X is a 0. Q1 is a 1. That's 0. That's 0, 0, 0, 0. So D2, which is right here, and the be our D2 is at 0 right there. That's what we just computed. So let's look at the excitation table of mealy. The mealy example 2. It has 6 equations. It has 2 outputs, Z1 and Z2. It's a little bit simpler though. Let's just check out J. J right here just equals Y. All right, so where's J1? J1 is this column right here. J1 is this column right here. J1 is this column right here. And here. Where's Y? Well, Y is right there. Y is right here. Y is right here. Y is right here. So we're just taking this 1 and copying it down, 0 and copying it down, 1 and copying it down, 0 copying it down. So that was the reverse engineering analysis, where we start right here and work our way up like this. But what about the other analysis, the design engineering analysis? What would it look like? How would we take this and use it to build a kernel map? What would the kernel map look like? Well, we would start, let's choose some output. Let's choose something complicated, J2. So where's J2? J2 is this column right here. Okay, so that's our output that we're interested in turning into a kernel map. So that's going to be the result of our function what would be the inputs to our Carnot map? Well, these would be the inputs right here and right here. So we'd have a Carnot map that would look something like this. We'd have 0, 0, 0, 1, 1, 1, 1, 0, and this would be Q1, Q2, and then we'd have another 4, by 4 Carnot map. And then up here we'd have X and Y. So we're basically just flipping this row and this row. So this first column right here is all zeros. So we just write down, let's see, 0, 0, 0, 0. This next one is 0, 0, 1, 1. Well, these two are flipped, but it's both the same value. So it's 0, 0, 1, 1. And then this one right here is 1, 1, 0, 0. So again, the fact that those rows right there are flipped doesn't matter. And this one is 1. Oh, wait. Yeah. This and this are flipped, but they happen to be the same. Okay. We lucked out. 0, 0. So what do we have? We have a implicant right here. Party of 4, and looks like we have one right here. So this one is what? It's Q1 X bar Y. And what's this one? It's not Q1 X. Yeah. Ordering those together, we have that equation right there. So that's the forward engineering analysis. So the next step is to look at the transition table. And we're going to do this for mealy at first. So the goal of the transition table in a reverse engineering fashion is to look at these values here and translate them up to here. And you can see they're all the same. I mean, this column is the same as this column. And that's because the D flip-flop directly follows the next state. Remember, D flip-flops are the easiest to design with. So if we're working down in the design fashion, we just redraw a transition table and it becomes excitation table. And if we're going in reverse, you just retitle this label right here, this column heading. That's it. Now, if it's a JK, then it's a little bit more difficult. And that's what we're going to see right here with this Moore circuit. You can see that this now is being translated into this. So how does that occur? Okay, so let's take something complicated like this one and look at how it turns into this right here. So this stands for J1 and K1. So we're looking at this pair right here. It's going to take this 0 right here. It's going to reset it. Well, it resets it to what? 0. All right, now let's look at this one. This is J2 and K2. It's going to influence Q2 by doing what? Well, 1, 1 stands for toggle. So it's going to take that 1 and toggle it to a 1. Let's try another one. Let's try this one right here. This is going to take this 1 right here and toggle it to what? A 0. The other direction is something we did at the end of chapter 6. Let's look at it. So from a design engineering point of view, let's start right here. And we're trying to take this and create this. So what would J1 and K1 have to be in order to take that 1 right there and change it into a 0. So our current Q is a 1 and our Q plus is a 0. So we could do this with a toggle, which would be a J value and a K value of 1, 1. Or we could do this with what? A reset, which would be a value of 0 and 1. So in the JK world, there's always going to be a don't care and a 1. So this right here should be a don't care and a 1. In fact, every pair right here, one of them should be a don't care. There should be a don't care here and a don't care here. I mean, I don't know what the pattern is. I mean, I could compute it, but every other one is a don't care. That's what makes JK powerful. And you can't see it in this reverse engineering direction. We can't see the don't cares. They were already determined when the circuit was built, when the kernel maps were done. Okay, so we're moving up towards the implicant table. Yeah. As we work our way up, reverse engineering this circuit, the big question is, what was this circuit for in the first place? We have no idea why we're even looking at this circuit. We're just troubleshooting it. We're just reverse engineering it. But we're getting to the point where we can see that information is lost, gone permanently, forever, unless there is a design document that documented this downward process in the first place. The circuit itself does not contain all the information necessary to recreate this process. As we go down, information is discarded. We discovered when we went down from the transition table to the excitation table, there were don't cares that don't show up when we reverse engineer it. Now we're going to uncover even more significant stuff that's missing, that we can never know, reverse engineering it. Now, in reality, these states have names, like names of cities or something like that. But we're just saying A, B, C, D, just random context-less names. So here's how it works. I mean, we just go through and we go, okay, so this is A, this is B, this is C, this is D. So wherever there's a 0, 0, that's an A now. And A, and let's see, B is right here, and C's here, and C's here, and then this is D, and this is D. So we've gone from the transition table back up to the state table. Yeah. And it's just about as easy going down in this direction. But what's different is the names up here have some context that relates all the way back up here to the original word problem. Here's another problem. This is a state table. We're at the implicant table step. Why am I calling this a state table? This is another loss of information that we'll never be able to recover going up. Let's just hold that thought for a moment and scroll up. Yeah, there's no difference. Just replace this with A, B, C, and then go through here, A, right? Where's another A down here? Yeah, AA and AA. Right, so there's no difference. So let's talk about this problem here. We're working our way up from a transition table to what we think is an implicant table, but we're basically skipping this step to a state table. But when you're going down here, you have to go through this implicant table, and what results is a minimized right here, state table. So the state table up here this is a big state table right here going into this step. And then we end up with a minimized state table. But we can't see that going up. We can't see the bigger state table. These steps right here are very similar to QMC and the Petrick method. That's why we went over it in the first place, so that you can do these steps. You're basically shrinking the circuit right here. Just like we shrink it when we go through these steps, through the kernel maps. We also shrink it right here. This is a shrinking step. So in reality, this state table right here should be much bigger, should be fluffed up. All right, so here's the mealy state table. And what we're doing is just repeating it. I mean, what else can we do? We're just reverse engineering it. So the same thing's going to be true for the more method. I mean, the two tables are going to be identical. Yeah. So this process of going from the implicant table to the state table is not showing any of this complexity right here. So we've got a whole section reserved for that coming up. Now the next step is to go from our state table to a state diagram. Well, obviously, this state diagram is going to be trivialized because we're working our way up reverse engineering. The word problem, this could be incredibly complex, and these would be names of places or people or events or motions or whatever the circuit's dealing with. And there's going to be a need to reduce this state table complexity here when we go from the state table to the implicant table. But we can't see that in this reverse engineering process. What I'm going to do is go through the self-talk of drawing the state diagram from the state table. So I'm focusing my attention down here on this A right here. And A, let's stick right here, goes to C when the input's a 0. So I'm going to put an arrow down here and draw a C. And I'm going to write down 0 because that's when the input is a 0, right? That 0 goes to C. I'm going to write a B over here, and it goes to B when the input's a 1. All right. Now I go over here, and when the input is a 0, it outputs a 0. So in mealy, what we do is we put a 0 right there. And when the input's a 1, it outputs a 1. So I'm going to put a /1 right there. All right, now I'm going to go to B. It looks like at state B, it goes to D no matter what. So it's always going to go over here to D. And it's going to output a 0 no matter what. So we would write down, okay, if it's a 0, it's going to output a 0. And if it's a 1, it's going to output a 0. But no matter what, it's going to go to D. So now let's go to C. So we're down here at C. If C is a 0, it stays at C. Cool. And let's see, what does it output? It outputs a 1. All right. Now, if we're at C and we get a 1, we go back to A. And so that's a 1. And we output a 0. All right. Finally, we're at D. We always go back to A. And let's see, if it's a 0, we output a 1, and if it's a 1, we output a 0. If it's a 0, we output a 1, and if it's a 1, we output a 0. Yeah, so now they look the same. So let's go look at the more version of this. All right, so we're going to start up here at state A. And it's going to go to state A itself if the input's a 0, 0. Right? Because it says A, if the input's a 0, 0, it's going to go to state A. Now, if the input's a 0, 1, it's going to go to state C. We'll put state C down here and say 0, 1. And then if it's a 1, 0, it's going to go to state B. B. And if it's a 1, 1, it's going to go to state D. One, 1. B was a 1, 0. Now, as long as at state A, it's going to output a 0, 1. Okay, B stays at B if it's a 0, 0. So it looks like these are all. Okay, and B goes to D if it's a 0, 1. And B goes to A if it's a 1, 0. And B goes to D if it's a 1, 1. So it goes to D if it's a 1, 1 also. Okay. C goes to C if it's a 0. 0, 0. C goes to B if it's a 0, 1. C goes to A if it's a 1, 0. It's a 1, 0. Or if it's a 1, 1. D stays at itself if it's a 0, 0. 0, 0. D goes to A if it's a 0, 1. D goes to C if it's a 1, 0. And D goes to A if it's a 1, 1. All right, so now let's change pin colors and deal with these outputs. The output is 0, 1 as long as you're at state A. So we're going to write a 0, 1 inside that circle. And the output's going to be 0, 0 as long as we're at state B. This is very different than mealy, where we had a slash and we talked about the outputs on these arrows right here. So at state C we have a 1, 1 as our output, and state D we have a 0, 1 as our output. So our output doesn't change until we arrive at the destination state. All right, let's wrap this up by looking at the word problem. And there's just no way to do this. And this is the toughest part of engineering, going down. Going up, there's just no way for us to recreate the word problem. This is a simplified version of the real state table. So we can't do this for the mealy or for the more. So summarizing, the hardest part is going from the word problem to the state diagram. Half your first homework assignment is going to be that. Just that. The only advice I have for you is look for patterns. Then once you get a state diagram, then you can create a state table. Once you get a state table, you've got to go through something like Quine-McCluskey method, and then a Petrich-like circuit reduction to get to a reduced state table. This is called the implicant table. And once you get to the implicant table, then it's just a ball rolling down the hill. You create state, go from the state names to cues, and go from the cues to the flip-flops, and then go from the flip-flops to the K-map, and from the K-map to the circuit.